Okay, welcome to lesson 6, the binomial theorem. This is our last lesson of unit 4, so congratulations, you've made it to the end. Make sure that you are asking questions if you get stuck on anything, and make sure that you have done the assignment on permutations and combinations that we had on Quest, because that is due on the 9th, if I remember correctly, on Thursday. So, Lesson 6, binomial theorem is, and specifically binomial expansion theorem is what you might hear some people refer to it as, kind of looks like the following. So if you have a binomial and you change the exponent by 1 each time, it causes a variation in our kind of expanded form. So anything to the power of 0 is 1, which is pretty obvious. Anything to the power of 1 is itself. That stays the same. Anything to the power of 2 then becomes a little bit more complicated. So with no coefficients in here, okay, so again, we get a squared plus 2ab plus b squared. So we see that a is kind of decreasing in exponent from 2 to 1 to 0. It's not there. B is increasing from 0 to 1 to 2. And my coefficients are 1, 2, and 1. Okay, so when we look at the next one, a plus b, or that binomial cubed, what ends up happening is we get the same effect. But this time we've got 1, 3, 3, and 1 is my coefficients. B is increasing from 0 to 1, 2, 3. And A is decreasing from 3, which is my matching exponent, down to 2, to 1, down to 0, because it's not there at all. Okay, so we've got some very specific patterns going on. When we look exclusively at coefficients, this is important because of our last unit, or our last lesson rather. I go 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Well, if I go back and look at Pascal's triangle, I'm getting exactly the same kind of thing. So when I get power of 0, I have no coefficients, so it's just 1. And then I've got, to the power of 1, I've just got a coefficient of 1 for each of them. Well, that's 1 and 1 there. And this continues all the way down. So essentially, our coefficients of each term are determined by Pascal's triangle. And so we can use our permutations, or specifically our combinations, to determine the coefficients of any term in a specific binomial power. Okay, so there are the following patterns. Okay, so this would be a helpful thing to kind of refer back to in terms of general patterns for when you have to like explain why Pascal's triangle is important on the provincial exam. Okay, so noting the patterns. Coefficients of the expansion are the numbers in Pascal's triangle. So that's the green highlighter up there. Okay. When the exponent is n, there are n plus 1 terms. So that's something I didn't mention, but we've got 1, 2, 3, 4, 5, 6 terms, and that's to the power of 5. We've got 1, 2, 3, 4, 5 terms, and that's to the power of 4. 2, 3, 4 terms to the power of 3. 1, 2, 3 terms when it's to the power of 2. 2 terms when it's to the power of 1, and 1 term when it's to the power of 0. So my exponent is always 1 less than the number of terms that I end up getting when I expand. The first term is a to the power of n, and the exponent of the power decreases by 1 for each term down to 0. The first term for b is b to the power of 0, and it goes all the way up to b to the power of n. This happens when the sum of the exponents in each term is n. So we can check that too. So 5 plus 0 is 5. 4 plus 1 is 5. 3 plus 2 is 5. 2 plus 3 is 5. 1 plus 4 is 5. And 0 plus 5 is 5. So that stands true as well. So these are all the general patterns that we see. So what does that mean? It means that we can actually figure out any term in a binomial, expanded binomial, based on this kind of formula for the binomial expansion theorem. Okay, so we've got x plus y to the power of n would give you n over, and then 0, because that's my first term. And so you'll notice it goes all the way up to our maximum. Okay, now what does this mean? We get some sort of crazy things going on here. Well, if we go back to our formula sheet for a second, bear with me. You get this general formula here. And it's a really big one. So for any specific term, and you can determine, let me just zoom in here. You can determine what that exact term for that binomial should be given this function. If the binomial is a plus b to the n, any term, we'll call this t, actually. Okay, if the binomial is a plus b to the power of n, okay, and k is 1 less than the term number, then we can plug this in. So we'll do some examples, but this is going to be your key piece here. So I'm just going to take a screenshot of it to bring it over. Okay, so in general, again, this formula is going to be what we can use to determine any term. So it says expand and simplify the first 4 terms. So instead of trying to multiply all of them out and simplify everything, I can actually use this formula. So term 1, that would mean that k would equal 0, right? Because it has to be k plus 1 gives me that term number. So I'm going to do n, which is my exponent. So 8, choose 0. And then a is my first term. Of my binomial. Okay, so it would just be x. And then to the power of n minus k, so 8 minus 0. And b is y, because that's my second term. And that's going to be just the power of 0. So I can do this. Anything choosing nothing is going to be 1, x to the power of 8, y to the power of 0 is 1. Okay, so it simplifies to that. Term 2, k equals 1, right? 1 plus 1 equals 2. And I always just write it like this so that I remember my k value is not the same as that subscript. Okay, so we've got 8, choose 1, x to the power of 8 minus 1, y to the power of 1. So this becomes 8, x to the 7, y for term 2. Term 3, k equals 2, and you're noticing a pattern here, I hope. 8 choose 2, x to the 8 minus 2, y to the 2. And I'd use my calculator to figure this one out. It gives me 28 x to the 6 y squared. And term 4, k equals 3. I'd do 8, choose 3, x 8 minus 3, y to the 3. And that would get me, use my calculator again, 56 x to the 5, y cubed. So those would be my first 4 terms. Okay, so again, we notice x is decreasing by 1 each time. The exponent, y increases from 0 to 1 to 2 to 3, and then these values are coming from my combination. Now, using this formula for this, it's always handy to identify as much as possible. So this whole thing goes in for A, and this whole piece here would be B. Your exponent is n. And this question actually isn't complete, so just kind of bear that in mind. I think it's supposed to just say expand, then simplify. So if we were to expand this the old way, ignoring this pink stuff, what I would do is I'd go 3b minus 1 times 3b minus 1 times 3b minus 1 times 3b minus 1. And then I would use FOIL to help myself out. I would group kind of these first two together and the second two together. So I'd end up with 9b squared minus 6b plus 1. And the same thing back here. And then I would multiply this through again. I would distribute it again. So first term gets multiplied through, second term gets multiplied through, and third term gets multiplied through. That would all give me 81b cubed, nope, not b cubed, b to the 4 minus 54b cubed, and 9b squared. Second one would give me minus 54b cubed, and then plus 36b squared minus 6b, and last but not least, another 9b squared minus 6b plus 1. From here, I'm not done because I haven't simplified. This is just the expansion part. If you did it one at a time, like you did this, and then multiplied its trinomial by a binomial, and then that answer times the binomial, that's totally fine as well. I just like to keep my steps as short as possible, so that's why I did it like this. So again, there could be other methods as long as it simplifies to end up being the same thing. That's the key here. So I've got my 1 b to the 4th term, so that's going to stay the same. We've got 81 b to the 4. I then have these two b cubed terms. So I'm going to put them together. That's going to give me negative 108 b cubed. I have these three b squared terms. That gets me 18 plus 36, so 36, 54. And then I've got 2 B terms. And finally, my lone constant at the end. Okay, so that's kind of how that all works if I expand it like that. That was tedious, it took a long time. You may find that the formula is just as tedious and takes a long time, but when we get into the bigger polynomials, like those guys up here, that's when things get a little bit tricky and it becomes even more tedious and time consuming, so it's nice to have that shortcut of using a formula. We do still notice here that it's true to our rules of decreasing b exponents. We don't see the same kind of symmetry through our coefficients though, and why that happens is because of that 3 attached to our first coefficient in our binomial. So this little 3 here really throws a wrench into the situation in terms of predictable symmetrical coefficients. But otherwise, we've got it simplified and we're good to go. Expand, then simplify this one. Well, let's see what happens here. And we'll do it the slow way. If you want to take a second, pause the video, remembering that we can write the expanded form like this, okay? But practice your actual expansion, your distribution, multiplication. It wouldn't be a bad idea. I'm going to pause my video, so I'm not going to walk you through all the steps and make you watch them, but I will post the solution and you'll be able to see it in just a second. So again, I can do this the long way by expanding my first 2 binomials and then multiplying by my last binomial through expansion as well, or through distribution. But as long as I remember that I need to simplify and combine those like terms, and always watch those integer signs of positive and negative. The key thing to note though is that we can apply this formula in every situation. So even though I spent that time expanding these pieces, I didn't have to. I could have used this same method. Okay, so again, another way to remember that k value is by looking at this exponent on the second variable is the key number, and it's always 1 less than the term number. Okay, and so we say k, it's kind of that number. You know what, this is worded a little bit differently. I'd prefer k plus 1 equals nck. And then again, a to the power of n minus k, b to the power of k. And so that k value is our exponent on b. So maybe we reword this. Yeah, 1 less than the term number is correct. Okay, so k is the key number. So applying this, not only could I do what I did in the first example there of finding the first 3 terms, I can use it just for very specific terms. So if I want to determine T9, that means that k is 8. Then I can do that by simply plugging and chugging. So again, this is n, this will be a, and this, including the value out in front, that negative there, is going to be b, filling in this formula. And again, this is the formula we're going to use because that's the one that shows up on the provincial exam, not this other format here. Okay, so bearing that in mind, we've got 10, choose 8. A is x, so that's nice and easy. 10 minus 8 and minus k. And b is negative 2 to the power of k, which is 8 again. So I'm going to need to use my calculator because I don't know this off the top of my head, and I definitely don't know this off the top of my head. But we're going to have 2 steps here, so make sure you've got enough room for 2 more lines. So we look at this and we're like, great, we're done. But you are not done because we've got 45 multiplying and 256 multiplying and our variable there. So what we're going to do is we're actually going to take those quote unquote like terms, those 2 terms that are coefficients that are multiplying together with our x squared, and we're going to multiply them. So I go 256 times 45, and I did not leave enough room for my answer here. That would be term 9. Okay, so that's what we see, and I didn't have to expand the whole thing. I didn't have to spend all that time multiplying all those terms together, and remembering to watch out for exponents, to watch out for my different integer signs of positive and negative, to watch that I make sure I multiply every term without fail. So this saves me a lot of room for error as long as I plug everything in properly. So again, A in general is your first term. B is your second term. N is your exponent, and K is 1 less than the term number. Okay, so those are general rules for this formula. So what does that mean if we have like a coefficient in our term? Well, it means that we do exactly the same thing, we just need to bear that in mind. So if we're finding the 6th term, like it asks in the question, that means K is 5. Then I'm going to go 15, which is N, and again, if you need to write it down, N is 15, A is my first term, so it's M, B is my second term, that's 2y, and K is 5. If you want to write it off to the side instead of writing it over here, do that. There's nothing wrong with that, and it might help in the long run. Okay, so plugging it in. Sometimes you like to write out the whole formula ahead of time before you actually start plugging values in. That's fine too. Okay, choose 5. Okay, the reason that I like to write my K value in here is because I have this predisposition to just grab this number otherwise. So if writing over here makes more sense, do that. If writing it in there in brackets makes sense, also you can do that. Okay, then I've got my first term, which is M to the power of N minus K. And then my second term, which is 2y, so I'm going to put it in brackets, and it's all to the power of k, which is 5. So what does that mean? How does that change? Well, I still have to solve for my combination, so that's nothing new. Plug that into my calculator, try and write the correct number. M is to the power of 10. What happens here is that when we have a power of a product, we can actually apply that power to both pieces. So I've got 2 to the power of 5, which is 32, and then y to the power of 5. Just like the previous example, whenever we have kind of constants that are multiplying in a string of things, we can pull them out and multiply together. So that's exactly what I'm going to do. Times 32. And that gives me 96,096. M to the power of 10, y to the power of 5. And that would be my sixth term. And you could even write T6 to help complete your answer. Okay. So it's just plug and chug. The trickiest part is that recognition that any coefficient and any sign need to go with your term. So again, here, B would include that subtracting sign, because in my original description, it's an addition binomial or a sum binomial. So we've got a few more examples. If you want to pause the video now and attempt them on your own, I strongly recommend it. I will work through the next one just because it's a little bit more intense still, but definitely I'm just going to post the full solutions at the end of the video for example 7, 8, and 9, just so that you really do get a chance to try them on your own. And if you have any questions, please always feel free to ask. So example 6, we're determining the fifth term. So again, if I want to list it all out ahead of time, n is 17, a is 3x. So again, we just saw a term or an example where we had a term that had a coefficient, so that's manageable. B is y squared. So this is what's new about this example, is that exponent. So we'll look at that when we start plugging everything in. And k is always, again, one less, so term number 5, so k is 4. I'm going to plug this into my formula. So 17, choose 4, 3x to the power of 17 minus 4, and y squared to the power of just 4. So again, that first part, I'm just going to plug in 17, choose 4 on my calculator to get 2,380. When I look here, again, 17 subtract 4 is 13. So I'm going to do 13, and I'm going to distribute that to both pieces. So 3 to the power of 13 gives me, on my calculator, a massive number. And just x to the power of 13. We've got another power rule happening here. This time, instead of distributing it through, we have a power of a power, which means we multiply. Okay, so 2 times 4 is 8, so that gives me y to the power of 8. Again, I'm going to look for things that I can combine. Constant, constant. I'm going to multiply those together. So multiplication doesn't matter the order that they're in. So times 2380. And this gives me a ridiculously large number. The fact that it's ridiculously large makes sense based on the size of these values. So I'm going to think that that's right. Oh, and make sure I don't drop that 1 in front of the 3, because that's a pretty high exponent. I'm not used to that. Okay, but we still apply the formula the same way. We just need to be conscious, again, that we're always selecting the full term to plug in for that a and b in our formula. Because a and b are just standing in for any 2 terms that make up a binomial. So pause the video and see if you haven't already. Give 7 a shot. This question is a little bit different. It doesn't give you the term number. So you know what, I will actually walk through this particular example just so that you can kind of see how you might approach it. Okay, so when I first read this example, example 7, find the term in the expansion of x plus y to the power of 7 that contains x squared. The first thing I can do, again, is list out those values that I want to plug into my formula. But the tricky part is that I don't know everything about the term number. I don't know the term itself. All I know is that it contains x to the power of 2. So that's all I can plug in, which means that's all I'm going to actually work with. So if I tried to fill this in, it would be like blank x squared y to the power of some number. I don't know these things yet. Equals, but then 7, choose, I don't know how much. Okay, this would be k as well. Okay. X to the power of 7 minus k, and then y to the power of k. So the only thing I know for sure is my x term, so that's all I can actually work with. The rest of it is kind of inconsequential. There's no x's anywhere else, so they can't influence my final value, so I can kind of disregard them. So I can look at this and say, okay, well, if it needs to be x squared, then it needs to be created from this piece of the formula because it's the only place x can come from. So 7 minus k. Well, that means that 7 minus k has to equal 2. So I can drop my base, ignore the x because it doesn't matter what the value is of it, and just look at the exponents. 7 minus k has to equal 2 in order for these two statements to be true. Which means that if we move it around, we get k equals 7 minus 2, which is 5. Remember, k is always 1 less than our term number. So term number is going to be 6. So that's how we can tackle it. Okay, so you're going to use this, you can use a very similar approach for example 8. It's even kind of quicker from where I'm standing, but if you want to give it a shot, just to kind of bear that in mind, give it a go. So again, we see in this example, if we list everything out, the only thing we really know about our term is that y is to the power of 8, which means that's all we can really work with to try and solve it. And there, luckily, is only a y in our second term. So this should be relatively simple, just like our previous one, and that we can't really work with x and we can't work with our constants because we don't know anything about them. So when we go to fill in our formula, we can just fill in with k's wherever we can and hopefully be able to deduce something. And we can deduce something because if we look at our y terms, again, everything in orange, we can't simplify because it's just sort of there and has k's attached to it, but I don't know what the k is. So I look and I say, okay, well, y to the 8, y only shows up there, so it must be equal to y to the k. Well, that means, oops, I'm getting ahead of myself here, the k must be 8, because otherwise that can't happen. So 8 equals k, which means that it is term 9, again, because k is always 1 less. Once we've discovered this part, you can actually find the whole term, and that's something that I forgot to mention for example 7. So when it says find the term in the expansion, it's great to determine the term number, but if we want to actually like determine the whole thing, we would plug back in here. So 7, choose 6, would be 7. X to 7 minus 6 is 1, and y to the power of 6. Oops, not 6. K is 5. Sorry. And again, that's how easy it is to simply plug in your term number. So again, that is not k, in case you're inclined to do that like me. So we would do 7 choose 5. Should be 21. X to the power of 7 minus 5 is x to the power of 2, and y to the power of 5. For this example, once we know it's term 9, again, we can plug in here. So it's going to be 10 choose 8, because 8 is my value for k. So it's going to be, so term 9 is 45, and then x to the power of n minus 8, or 10 minus 8 is x to the power of 2, and y to the power of 8. And that verifies what I wanted. Just like up here, I wanted that x squared term, and that's exactly what happens. Okay, so this last one, again, feel free to pause and kind of give it a shot on your own before coming back to me working through it. Okay, so again, by listing this out, it kind of helps me fill in my formula. So I don't know the term number or the coefficient for the term. That's fine, but I do know about the variables. So I'm just going to leave out the part that talks about the term number, and I'm going to look at my variables and their exponents. So I have two situations here. I have a situation where I know that x cubed needs to be equal to x to the power of 10 minus k. I also have a situation where y to the 7 needs to be equal to y to the k. Bearing this in mind, I can set up two equations. X to 3 equals x to 10 minus k. And again, I get the similar situation as example 7. So I can say that 3 has to be equal to 10 minus k. And so k equals 7. I can check this by also looking at y and seeing if I get the right solution there too. So y to the power of 7, not 5, not sure where that came from, equals y to the power of k. So k has to equal 7, where 7 has to equal k. Because these both match, I can feel very confident in my answer that k is 7, which means that I'm looking at term 8, and I'm going to plug in this value for k. And so plugging it in here. So 10 choose 7 is 120. Then I've got x to the power of 10 minus, and all the rest of it should match up, but just to double check that I've done my math correctly, 10 minus 7 is 3, so x to the power of 3, and y to the power of 7. So that would be your final answer. And that's our last example. So I'll be posting some worksheets to go with this, with the idea of some practice in using binomial expansion and that formula to kind of predict what terms might be, and if you were given a specific term, what would its number be, where would it be situated in the whole grand scheme of things if the whole binomial was expanded. So again, ask questions as they come up. This is kind of an abstract lesson. It sort of stands alone. We need combinations in order to do this math. That's really why it's included in this unit. But otherwise, it is a little bit different than anything else we've seen previously. So please be sure to practice this. And then there is a review posted in our Office 365 folder, so you can take a look at that. And then write your test as soon as possible, because our exam is coming. It's June 11th.